Hello, this geometry video is about conditional statements. We're going to go over just an if-then statement, regular conditional statement, the converse, inverse, and contrapositive, and also look at shorthand notation for that, and the biconditional statement. So this is a lot to cover. It's pretty easy though. It's just kind of logic and the basis of logic that we use in geometry, right? Euclid wanted to say, well, if something is true, then what's the next step that I can conclude something that has to be true on top of that? So if we know what a point is, then I can start talking about a collection of points to make a circle. Or if I know what a segment is, I can put those together to make a quadrilateral, right? And stuff like that. So we need to kind of know if and then statements. And this goes right into proofs too. The very next step from this is the introduction to two-column proofs and other types of proofs, flow proofs and other things. So let's get into it. So if the and then are the two words that you're going to see in here. There's an if and a then, right? The if part we call the hypothesis. That's the part that is kind of the truth. Like you're trying to match this up to begin with. If you have this truth, this hypothesis, if the hypothesis is true, then the conclusion must be true. Now that's saying that if the statement is true to begin with, right? So that's what we're always looking for, is trying to prove if statements are true. And if they are, we can use them in different circumstances and situations. So if it is Friday, then the cafeteria serves gyoza. I think this used to be true, but I don't think it is anymore. So like today is Friday. It actually happens to be Friday for me when I'm making this video. If it is Friday, so that part's true. The cafeteria serves gyoza. Well, that part's false for me, but it is what it is. So this is a false statement. We can't use it to like in a proof or to prove something else. Like we can't use it. It's not a good statement, but sometimes they are. And the statements we've found to be true, we want to use those in proofs to prove other things. Okay, so right now we're just practicing if and then, right? We're just practicing if and then. So if we have this geometrical sentence here, vertical angles have the same measure. This is a true statement, but it's not really in the if-then form, right? So if you have vertical angles, and we would rewrite that, right? If you have vertical angles, those are the ones that are across from each other, up and down or left and right, then they have the same measure. So it's the same sentence. We're just throwing in the if and then to it so that we can really identify what's the hypothesis and what's the conclusion. That's important because when we do the converse and the inverse, things are going to get flipped around, are going to get switched. And sometimes when you switch things with the converse, the statement isn't true anymore, right? So like, let's say I read this one backwards. If they have the same measure, then two angles are vertical angles. Well, that's not necessarily true. Just because two angles are equal doesn't mean they have to be vertical to each other. But the way it's written now, if they are vertical angles, then they have the same measure. That's 100% true. That's something that we've proven in geometry. So, and we've kind of established. So now I could use this fact to go on, like in a longer proof, to prove other things, like to connect different things together, right? That's what we're talking about. All right, let's keep going. So counterexamples. Now, usually we're looking for truth in things and we're trying to prove things using statements. So what if you wanted to say, well, I know this statement isn't true. Like the previous statement we had before was, if it is Friday, then the cafeteria serves gyoza. All I have to do is go to the cafeteria on Friday and see if they have gyoza. And if they don't, then that would be what we call a counterexample. This is something that disproves the statement. The important part is that the first part is true. Even when you're disproving it and using a counterexample, the first part has to be true. So you can't go on Thursday and check to see if they serve gyoza. That wouldn't make any sense. You have to go on Friday to see if they serve gyoza if you want to prove this statement false, right? So same thing here. If you smoke, then you'll get lung cancer. I don't want to take someone who doesn't smoke and then try to talk about whether they have lung cancer or not. That's not going to help me disprove this statement, right? I want to find somebody who smokes. I could use my brother Phil. So Phil, my brother Phil, who smokes, but he doesn't have lung cancer. So I've shown you a counterexample that if you smoke, then you will get lung cancer. Now, I don't know if you will in the future, but I've proven that not every single person who smokes will get lung cancer. When you're doing conditional statements in mathematics and Euclidean geometry, it has to be universal. It has to be 100% for all cases, not sometimes. So if you ever find yourself with a sentence where it's like, well, it's sometimes true, but sometimes not true, well, then it's false. If you can find one counterexample, then you've proven that statement false. Let's look at, this is a good example for that. So the next one here, if x squared equals 16, then x equals 4. Well, that's actually true, but they're saying if x squared equals 16, then it has to be, there's only one option that x equals 4. But I know there's another option. I could have x equals negative 4. What if x was negative 4? Then x squared would equal 16, which would make that first part true. So I found a counterexample. I found something that makes the first part true, but doesn't match up to the second part. It doesn't make the second part true. That is a counterexample. This statement is false. Just because x squared equals 16 doesn't mean that x has to be 4. It could be negative 4. And this is what I was talking about. This is that sometimes situation. Well, sometimes it's 4. Yeah, but it's not always 4, right? It has to be always 4 in order for the statement to be true. All right, moving on. Okay, now this is what I was talking about before, where we're switching things around. So in logic, you start to play around with sentences and start to flip things around and stuff. So this is what if you took your conditional statement? So let's take this one. If an angle measures 90 degrees, then it is a right angle. Well, we know this to be true. So first part true, you got a 90-degree angle. We call that a right angle. We've defined that. That's just what we've defined it as. That's the conditional. This is just regular conditional, nothing special. Now, what if we do the inverse of that? Now, the inverse, what it does is negate it. So when we say inverse, we're saying let's make everything not. It's the not part of it. So if an angle does not measure 90 degrees, so I've got anything else besides 90, like 80 or 45 or whatever, right? Anything that's not 90, then it is not a right angle. Well, that's probably true in this case. It doesn't always have to be true, though. Just because the conditional is true doesn't mean the inverse is always going to be true. Sometimes the conditional is true and the inverse is false, right? You just have to read what you have. So if an angle doesn't measure 90, then it does not form a right angle. All right, so that's the inverse. Now we have the converse and the contrapositive as well. The converse, let's go back here. The converse is going to take the if part, the red part here, and the green part here, and it's going to flip them. All right, it's going to flip them. So I think of it like Converse shoes, like you have a left shoe and a right tennis shoe, and you take your left shoe and your right shoe and you switch them and put them on the wrong feet. So if you ever forget, like, which one's the Converse? Well, just think of shoes and a left foot and a right foot, and you switch your left foot and your right foot. I don't know, it's cheesy, but maybe you'll remember it. So if an angle is a right angle, right? So we've started with the right angle part, then it measures 90 degrees. Well, that's true too. Doesn't always have to be, but it is in this case. If an angle is a right angle, then it measures 90 degrees. Yeah, if it's a right angle, there's no other option, right? Okay, contrapositive. Now the contrapositive does both. It will do the inverse with the negation, and it will also do, it'll also do the converse at the same time. So it's going to flip the shoes, but it's also going to negate them. It's also going to make them negative. So if an angle is not a right angle, so something that's not a right angle, so it's got to be some other angle besides 90, then it does not measure 90 degrees. Well, that's actually true, right? If it's not a right angle, that means it has to be something else, like 80 or 45 or something. So the next part says that it does not measure 90. Well, we know that. It doesn't measure 90. It measures something else, like 80 or 45 or whatever. Okay, so that's true. And what you're going to find in logic, and that's why even if you're not in mathematics, but you're just doing logic type stuff, for like truths, like if you're doing lie detecting stuff and you're into kind of human behavior and that kind of thing, and you want to give someone a statement and then give them a different version of the statement and try to catch them in a lie, this kind of thing can be useful. Why? Because if a conditional statement is true, then we know that the contrapositive will also be true. And that works both ways. So sometimes if you're reading a statement, like an if-then statement, and it's kind of hard to understand the way it's written, sometimes you can flip it around and negate it, do the contrapositive of it, And then sometimes it's easier to understand. Like if you flip it and then negate it, if that statement is true, then the original statement has to be true, which is kind of weird, but it will always work no matter what. You'll have to play around with it and try. And then also the inverse and the converse. It's kind of weird, but those will also be the same. Like if the inverse is a true statement, the converse will also be a true statement every time, and vice versa. If the converse is true, then the inverse will also be true. Whoops, the inverse. So conditional and contrapositive are related to each other, and the inverse and the converse are related to each other. These are not related. Like if the converse is true, the contrapositive could be false, could be true. We don't know. There's no connection there. Okay, this is shorthand notation. So those are all the different types of statements we're going to use, except for biconditional. We still have biconditional to talk about. But this is just a shorthand notation for each of those. A lot of times, instead of writing the whole sentence out, we'll just use P and Q or T and R or S and W or whatever. It doesn't matter. We'll use some small letters and just make them equal to something. So we'll say, oh, P is I'm thirsty, and Q is I will drink tea, right? So if I'm thirsty, then I will drink tea. And we use this arrow just to kind of show that this is an if-then situation, right? So if P, then Q. We use this little squiggly mark to show the negative, the not. So if I am not thirsty, then I will not drink tea, right? Something like that. And then here we switched it around. You can see the converse is where we take the P and the Q and we just switch them. So if I drink tea, then I am thirsty. And the contrapositive does both. So we got the negation, but we also took the Q and the P and we switched them. So same thing as before, just shorthand notation. If I don't drink tea, then I am not thirsty, right? Okay, so you got to get used to that. Just kind of go with it. A lot of times you'll have these defined, like P represents something and Q represents something, and then they'll just use shorthand notation the rest of the time. Mathematicians are lazy, right? So we like to kind of write things in shorthand notation if we can. So we define things to begin with, and then we just use the shorthand notation after that. So you kind of have to roll with it a little bit. All right, last thing I think is biconditional statements. A lot of people have trouble with biconditional statements, trying to understand these. They get too hooked on things have to be one way or the other. Or like if you look at a conditional statement, a lot of people think this is backwards. You can read it backwards, and that's not true. Let me try to think. Do we have a good example here? This is actually an okay statement. Just trying to think of something where if I read it forwards, it's true, but the converse is false, right? So, boy. Oh, yeah. Okay. How about if I drink poison, then I will die, right? If I drink poison, then I will die. Now, if I take the converse of that, right? If I die, then I drank poison. That doesn't have to necessarily be true, right? So if I drink poison, for sure I'm going to die. There's like no option. I'm not going to live. If I drink poison, I'm going to die, right? I mean, I know there's always like some kind of assumptions that go with that, right? Like the assumption is I didn't make it to the hospital on time. The assumption is I don't have an antidote. The assumption is, right? There's always assumptions that go with these statements, and that's why Euclid started out with his point, line, plane. Those were his assumptions to start off with, right? So we always have assumptions, and maybe you want to write those down sometimes. That's good logic. So assuming I can't make it to the hospital, assuming I don't have an antidote, then if I drink poison, then I will die. Okay, then we can say that's a fact then. If I do the converse of that, if I die, then I drank poison, that's not necessarily true because I could have died many ways. I could have been in an airplane crash. I could have, got run over by a car. I could have got a heart attack, right? Or whatever. There's many ways you can die. So that converse isn't true. So when you see an original conditional statement, the converse isn't always necessarily true, right? You got to be really careful of that. Now, if you do have a statement where the conditional and the converse are both true, which is what you see in front of you here. So if segment AB plus BC equals AC, I mean, just think of it like you've got like a segment, right? So you've got like from A to B. Let me see if I can get a pen here. Can maybe draw this out a little bit. So if I have a, oops, that's not very straight, but just imagine that's a straight segment and I've got 3 points on it. This is a really bad pen for drawing. Okay, but let's just say I do. Oops, I didn't want that either. Okay, and this is my A, this is my B, this is my C. Okay, so I got the distance from A to B plus the distance from B to C equals the distance from A to C. Well, that's a true statement. So if that's true, then they're saying that B lies between them. And that's actually a definition in Euclidean geometry, that if you use this word between, that it's actually on the straight line distance between those 2 points. So B is between them. So this is a true statement. And I can write it the other way too. If I were to reverse this and say if B lies between A and C, then AB plus BC equals AC. That is the converse of it. And this converse, so if B lies between them, then AB plus BC equals AC. Well, that's true too. So if you get a statement where the conditional statement and the converse are both true, then you can combine them. Remember I said mathematicians are lazy? This is another way we're being lazy. We're going to take both statements and we're going to put them together into one statement, so we don't have to write both statements all the time. We can just write one statement and we'll know that the original and the converse are both true. So a biconditional, we're going to take this if part out. We're going to take that part and take that out, and we're going to take the then part and take that out, and we're just going to use, let me copy and paste this down. I'm going to get rid of the, I'm going to get rid of the if and get rid of the then. And in the middle of this, I'm going to put this if and only if. If and only if. Okay, this is a little special right here. The little something a little different. It's when you see that if and only if, it's going to tell you that you could read this forwards or you could read it backwards and they will both be true. All right, if it's a true statement, right? Sometimes you have biconditionals that aren't true, right? But yeah, you sniff those out and stuff. But if this is proven to be true and someone's telling you I have a true biconditional statement, you know that the original statement and the reading it backwards, the converse, will also be true no matter what. So that's a biconditional statement. You got to be really careful with that. Some people get that really confused. They don't understand it. So if you don't, make sure you go ask your teacher questions and figure it out. Now, this if and only if, sometimes you'll see it as IFF. Though, again, mathematicians are lazy. They don't even want, we're so lazy, we don't even want to write out if and only if. We're going to shorten that to IFF. So you might see it as IFF sometimes if somebody wants to shorten it up. All right, so here's an example. IFF is in the middle there, this if and only if. And you'll notice there's no if in the beginning, there's no then in the middle. If you mix those together, you're going to get those wrong. It's just not going to be correct notation. So if you see if and only if in the middle, this really represents two sentences at once. It represents, let me it's easier to copy paste this down a little bit. Okay, we're going to get rid of the if and only if part of it and put in a then. In the beginning, I'm going to put in an if. So that's one way of writing this. If a polygon has exactly 4 right angles, then it is a rectangle. Right? And that would be a true statement. Like if I know this original biconditional is true, then I know that the original statement would be true. And I also know that the converse, I got to do the converse of this now. That means I got to cut this and flip it and take the last part and put it in the front, flip it around. That's the converse now. So now I also know the converse is true. So if a polygon has exactly 4 right angles, so think about a polygon that has 4 right angles. Well, that's going to be a rectangle for sure. And then if I read it backwards, so if it is a rectangle, then the polygon has 4 right angles. Well, that's true too. Rectangles have 4 right angles. So an if and only if biconditional can be read both ways. And if the biconditional is true, then both of these will be true. Okay, so that's a lot of stuff, right? Biconditional, make sure you understand those. Make sure you understand your shorthand notation. You need to know all 4 different ways of writing conditionals. You got conditional, inverse, converse, and contrapositive. And we need to know counterexample, and counterexample comes up a lot. It's very powerful. You need to be able to draw counterexamples. You need to be able to interpret counterexamples and to come up with counterexamples. And understand, whoops, went too far. Understand the hypothesis conclusion idea that you have to match up the first part and then use the second part to kind of prove things are true or not, right? And which we're going to be doing in proofs, which is coming up. Okay, thank you very much.